All right, we're going to wrap up this discussion on conformations, especially with cyclic compounds, by spending a lot of time with cyclohexane. And this is simply because cyclohexane can adopt a number of conformations, but we're only focusing on like two, and even then, a majority of the time we're focused on just one main conformation. But within that conformation, there's a whole lot of different issues with stability that we're going to have to discuss. Now, with cyclohexane, if we were to just draw the Lewis structure of it, we draw a hexagon. And if you were to try to build a model kit of cyclohexane, and I recommend you do this, build a model kit and try to lay it flat. You'll notice like your bonds kind of bend a little bit. Yeah, I kind of have to force it to be flat. And if you look around and two carbon portions, you'll see that all the hydrogens are eclipsing. And plus, if you kind of remember your geometry, um, this angle of cyclohexane is 120 degrees. So that's not the optimum 109. So rather what cyclohexane does is it will adopt a conformation, which we call a chair conformation, in which it is not completely flat. There are four carbons which lie within the same plane. And then there are two carbons that are outside. There's one that's up, that's kind of like the headrest, why they call it a chair. And then there's one that's down below those other four, and that's like the footstool of a chair. And that's why they call this the chair conformation. Now, again, to back up, if cyclohexane were flat, all of the hydrogens would be eclipsing. But if we look at the chair conformation, all the hydrogens are staggered. In fact, let's draw the not Lewis, the Newman projection for cyclohexane. It's a little interesting. I'm going to put in the hydrogens. And you can see in this conformation that all of the hydrogens, all of the groups, and even the carbons, like these CH2s in the back, I'll draw the hydrogens here. So the CH2s in the front and the back. Um, all of those groups are staggered to each other. There's no eclipsing hydrogens. Now, what cyclohexane does is it will go from one chair. And let's say, let's take this little footstool that's right here, and we flip it upwards, kind of like a rotation. Now, you can't rotate single bonds 360 degrees in a ring, but we're taking that carbon and doing a little bit of a rotation and flipping it upwards. And it goes to the other kind of, I'll say, for lack of a better term, popular conformation of cyclohexane, known as the boat conformation. And when we take that footstool and flip it up, notice what happens with the boat. In the boat, you got eclipsing hydrogens. You can kind of see those in the front here. You got hydrogens that are eclipsing. And you got these right here. We call them flagpole interactions. So there's like a little bit of sterics going on there. So the boat is a lot less stable than the chair conformation. And then what the boat proceeds to do is it will take this opposite kind of flagpole carbon and flip downwards to get to the other chair. And so this carbon, I'm going to mark it here with a little bit of a different highlighter. This carbon right here used to be the headrest. Now it's the footstool. And this carbon, oops, not that one. This one used to be the footstool. Now it's the headrest. And cyclohexane is constantly undergoing this chair to boat to chair, opposite chair, what we call it a chair flip, basically. And you can see in this energy diagram, um, first of all, kind of the numbers that are assigned with it. And don't worry about like this half chair, twist boat. Don't worry about those. I don't really kind of care about those a whole lot. The ones that we kind of worry about the most are the chair going to the boat and then to the opposite chair. Now, why do we care about the fact that there are two of these opposite chair conformations? Well, up until now, I've just been discussing cyclohexane, and all of these atoms that are attached to it are just hydrogens. One thing I do want to make you kind of make a note of, look at like these hydrogens right here. Notice how they're going straight up, straight down. And notice how these are kind of coming out to the side. Okay, kind of make a mental note of that, and we'll come back to it. So why do we care about these, about chair flips and all of that? Where it really starts to matter is when there are groups other than hydrogens attached to cyclohexane. That's when stability starts to change for the chair conformations. So before I get to that, you really need to practice drawing the chair conformation. So here's how one of the best ways I've found is draw two parallel lines that are diagonal in one of the directions. You're going to connect the top of the lines with like a V, like that. And then you're going to connect the bottom of the lines with an upside down V, like that. Now, if you want to draw the opposite chair conformation, so it's an equilibrium, just draw the diagonal lines the other way and do your V and upside down V to connect them. Now, do that over and over and over again until it kind of becomes second nature. Now, the other important thing that you need to do is you just have to like commit to muscle memory, is distinguishing between the two types of hydrogen positions, not even hydrogen, I'll say substituent positions on cyclohexane, because there are two sets of positions that are noticeably different when it comes to stability. These positions are known as axial, which is either straight up, and actually I'm not going to use hydrogens, I'm just going to put axial, or they are straight down. If we go back to our Newman projection, we can kind of see those hydrogens here. You got a hydrogen right here, axial, that's straight up, and one here, axial, straight down. Now, the other set of positions that you need to know is what are known as the equatorial position. And those kind of go straight out from cyclohexane and form like an equator or a ring around it. Now, as kind of a convention, at least for myself, the easiest way I've found to like recognize like where do I start with labeling axial and equatorial? I always start in the upper right-hand corner. So I'll mark that here with a dot because I know it doesn't matter which chair. I know that axial is always up in that upper right-hand corner. And here's the trend that you should know. If axial is up on one carbon, the next carbon over, axial is down. And then the next carbon over, axial is up. And then the next carbon over, axial is down. And then axial up, and then axial down. So notice the trend there. Now, the other important thing to note is that, and I'll go back to that carbon with the red dot there. In this case, the axial position is up. We say the equatorial position here is down. And I say it's not straight down. I don't want you to get this in terms of like straight up or straight down. It's kind of in a downward direction compared to that axial group. And I would say the same thing on the next carbon. This equatorial position is sort of up because it's more upward than this axial carbon here. I'm sorry, axial group. And then next carbon over. Notice how this is like a similar trend. The direction is kind of switching every carbon. This equatorial position is down, and then this one is up, and then this one is down, and then this one is up. Again, when it comes to the equatorial positions, we don't mean straight up or straight down. What we mean is that if an equatorial position is up, it's up in relation to the axial. So it's kind of like going upwards, so to speak. But what you need to do is do this over and over and over again. Just draw the same chair like 10 times and then label all the axial and the equatorial positions. Do it over and over until you get, until it just becomes muscle memory. Now, one thing that I want to highlight here is when a chair flip occurs. So whenever you do a chair flip, all axial positions become equatorial and vice versa. This will be a little bit more obvious when we start putting groups other than hydrogens on cyclohexane. So let's go to our opposite chair now and draw on the axial and equatorial. Again, I always start in the upper right-hand corner because I know for a fact in that corner, axial is always up and then equatorial is down. And then next carbon over, directions flip. Axial is down, equatorial is up. And then here, axial is up, equatorial is down. And then here, axial is down, and so on. It flips every single carbon. So like I said, you need to get proficient in quickly being able to draw chair conformations and quickly being able to recognize axial and equatorial and draw and even draw those in the right directions. So let me show you something, students try to do is when they draw something like say on their exam and they're like, oh, I think I'm just going to do this, you know, and what is that? Is that axial or equatorial? Because axial should be straight up. Equatorial should be like this. So that doesn't really count as anything. Like, try not to you can't really pull one over. So you need to make sure that, and I always recommend students, if you want to show a specific group equatorial, draw in the corresponding hydrogen in the axial position. Because then when I look at that and grade it, I'm like, oh, okay, that CH3 is supposed to be down. Now, the another an improper way to draw that would be to put like, yeah, that's a great axial hydrogen. This is not an equatorial group. It's not straight down. Okay, the equatorial groups form an equator around cyclohexane. It becomes a lot more obvious when you build a model kit. Look at these blue atoms over here. You can kind of see they form a ring around cyclohexane. And that's the direction that you should draw them in. Okay, so again, do this over and over and over and over. I can't emphasize enough. Just draw cyclohexane and then label your axial and equatorial positions. Now, up until now, we haven't been dealing with specific things other than hydrogens on cyclohexane. And if all there is are hydrogens, there is no difference between axial and equatorial if the only groups on cyclohexane are hydrogens. So there's no difference. When I say no difference, there's no difference in terms of energy or stability. But here's the interesting thing. When we start putting groups on cyclohexane, we notice that there is a change in stability. So let's compare. I'm just going through mono substituted, meaning one different group. So we're going to compare a bromine in the axial position versus bromine in the equatorial position. Now, I'm going to show you how I got here in a little bit, but let me show you the numbers first, and then that way we can kind of prove that there's a difference between axial and equatorial. In this equilibrium, going from one chair to the other chair, if we were to take a snapshot of of bromocyclohexane, 30% of the molecules would be in the bromine would be in the axial position, and 70% would be in the equatorial position. And this shows evidence that groups in the equatorial position are more stable than in the axial position. So why is this? Well, let's just look at when bromine is axial. So I'm going to redraw the chair here. So when bromine is axial, I want you to think about the size of bromine. Bromine is a massive atom, and it interacts not favorably with the other groups in the axial positions in the same direction. It doesn't matter if they're hydrogens. This bromine, think of it as supermassive like this. Well, that's encroaching on this hydrogen, and it's encroaching on this hydrogen. What do we call that when atoms are forced to be closer than they want to be? Steric strain. And this specific type of steric strain is known as 1,3 as a 1,3 diaxial interaction. Now, what the 1,3 means is that the groups are 3 carbons away. So if there is a group, any group besides hydrogen in an axial position, it is less stable than if that group were in the equatorial position. Okay. Now, one thing I want you to note here, and this is one of the most common mistakes students make when they do a chair flip, is notice I did not just take the bromine off and flip it with the hydrogen. I did not do that. Okay. Because if I were to just do that and then put it on this here, like this, notice what direction that bromine is going in. Here, that bromine is going upwards. Here, this bromine is going downwards. If I do a proper chair flip, the bromine, even though it flips what position it's in, it's still going in the same direction. So how do you do a chair flip properly? I'm going to demonstrate that here. Okay, so I'm just going to use X as a generic group. And what I want you to do is label the carbons here. Start number 1, always here. Just start there. This numbering has nothing to do with nomenclature. It's just a locator. And here's why I recommend just always starting with 1 in that upper right-hand corner. Because when you do a chair flip, you're going to take number 1 and flip it down, and that becomes the footstool. You're going to take number 4 and flip it up. That becomes the new headrest. So in the chair flip, So notice my chair now goes in this direction. This is carbon 1 right here. And then you just kind of number clockwise from there on out. So if this group were axial before, it's now equatorial. Still going in the same direction in terms of up versus down. So that is the proper way to do a chair flip. And you're going to have to know how to do this because and you'll see this in your homework set and also on an exam. I'm going to want you to draw both chair conformations of a substituted cyclohexane and then be able to choose, predict, I should say, which one is more stable. Okay. Now, with monosubstituted cyclohexane, that's easy. You want the group, the big group, to be equatorial. Where it gets a little more complicated is if there's more than one group on cyclohexane. So we're going to go now to disubstituted, meaning two groups on cyclohexane. So let's start from a skeleton formula. And just by the way, Me there is shorthand for methyl, so CH3. Now notice that those two groups, the chlorine and the methyl, have a specific direction. When we're dealing with rings like this, I know that we've talked about these dashes and wedges with like Newman projections. And so the solid wedge means the group's coming out at you. The dashed means it's going away from you. On a ring, it still represents directionality. But what the solid wedge means here is that group is going up and the dashed wedge means the group is going down. Now, why is that important? Let's draw a chair conformation for this. So practice your chair. And I always just kind of start with this carbon as number one. 1, 2, 3, 4, 5, 6. And then notice how that just winds up like this. 1, 2, 3, 4, 5, 6. Again, this has nothing to do with nomenclature. Now, the chlorine there, the problem says that that chlorine is going up. So on carbon number 1, I have to draw the chlorine in the upward position, which just so happens to be axial. You said, wait a second, don't you want it equatorial? Yeah, let's see if that matters here. Okay, we'll get to that. And then the methyl group is down. So on carbon number 2, the downward position is axial. All right, so now let's do a chair flip. Because you should start to imagine like, oh, wait a second, if both of those groups are axial, if I did a chair flip, that would put both of them equatorial. That would be a lot more stable. So let's do a chair flip, and we're going to do a proper chair flip. So I'm going to take carbon number 1, flip it down to become the footstool. Carbon number 4, flip it up to be the new headrest. So now this is 1, 2, 3, 4, 5, and 6. So carbon number 1, the chlorine is going to be going upwards. Again, when we say upwards for those equatorial positions, it just means it's going more up than the corresponding axial position. And then the methyl group should be going up, I'm sorry, down, which in this case is the equatorial position. Now you should be able to do this. Put the groups in the proper positions in one chair and then do a correct chair flip. The other thing that you should know how to do is recognize which chair conformation is more stable. In this case, it's kind of easy to see. Here, both groups are axial. You have two axial groups. In here, you have two equatorial groups. So this one is more stable. The equilibrium would favor that chair conformation. So the one on the right. Now, that's kind of the easiest case where you have all groups axial versus all groups equatorial. What happens if that's not the case? So I'm going to use the same compound, but in this case, both groups are up. So again, I'm going to keep everything conventionally the same. I always start my numbering in the upper right-hand corner because that's just the easiest for me to remember. What positions are which there. So now the chlorine, again, is going to be going up, which is axial. And the methyl group is going to be going up. In this case, it's the equatorial position. Now, if you look at that, you should already be predicting, well, if I have one axial and one equatorial, I'm just going to get the same thing when I do a chair flip. Okay, put that in the back of your mind. Let's do our chair flip. So I'm going to take carbon number 1, flip it downwards to become the footstool. 4 is going to go upwards to become the new headrest. And I'll number my carbons. 1, 2, 3, 4, 5, 6. So now the chlorine will be equatorial. And the methyl group is going to be axial. Again, we have one axial group and one equatorial group. So how do I figure out which one is favored by the equilibrium? Since the two groups are different, we need additional information. If they were exactly the same, then there would not be a difference in stability. So if they were both chlorines, we wouldn't care. They'd both be equally stable. But since they're not the same group, we need to know something called the axial strain energy. And this is something that you'll look up or you'll be given to, like on an exam or on homework problems. You'll be given the axial strain energy. So, you kind of look up in a textbook. There's usually a good table in every textbook that has the axial strain energies, or you can Google, axial strain energies, and there'll be a big table there that has, hundreds of different groups. I'm exaggerating, but a lot of different groups. And what the value that you're given is like how much it increases the stability of, or yeah, increases the instability, increases the energy of cyclohexane if that group were axial. So for chlorine, if chlorine is axial, it increases the energy of cyclohexane by 2 kilojoules per mole. If methyl were axial, it would increase the energy of cyclohexane by 7.6 kilojoules per mole. So the rule of thumb for a dye-substituted cyclohexane, if you can't put both of them equatorial, you want the one that has the highest energy to be equatorial. So we want this group, the ethyl, to be equatorial. So what does that mean? That means this is my more stable conformation of cyclohexane because it puts the methyl group equatorial. That one has the highest axial strain energy. Now, probably the most complicated is when there are multiple groups on cyclohexane. We call this polysubstituted. Basically, anything bigger, anything more than two groups is polysubstituted. So let's look at this as an example. So we're going to use an ethyl group, a methyl group. Again, in this case, ET means ethyl. And then we'll put a chlorine. Now, I'm going to number again, starting at the top, 1, 2, 3, 4, 5, 6. Because when I draw my chair, my first chair, I'm always going to make that upper right-hand corner number 1. So now let's put the groups on. On carbon number 1, the ethyl is up. Okay, that means I have to put ethyl up here, which just makes it axial. Carbon number 2, the methyl is up, and on this position, the methyl would be equatorial. And then I go all the way to carbon 5, and that chlorine is down. So over on carbon number 5 there, that chlorine is equatorial. Now we're going to do the chair foot. And already in your mind, you might think, well, if I have two groups equatorial, that should be better than one group axial, right? Um, don't always assume that. It might be true sometimes, but not all the time. We'll kind of, I'll show you how you can figure that out in a little bit. But let's just draw the chair foot real quick. So again, carbon number 1 is going to become the footstool. Carbon number 4 is going to become the headrest. And I'll start numbering now at the lower right-hand corner. So on number 1, ethyl becomes equatorial. Still going the upward direction, but it's equatorial now. Number 2, the methyl is now going to become axial. And then number 5, that chlorine is now going to become axial. Now, in order to figure out which conformation is more stable, I have to look at the axial strain energies. Again, you can't always assume that because the one on the left has two equatorial groups, the one on the right has two axial groups, that the one on the left is automatically more stable. You have to do the calculations. You have to look at the values. So we already have done chlorine. Chlorine is a value of 2. Methyl, I think we did that one on the previous page as well. That's 7.6. And then ethyl is 8. So what do you do with these values? You just add up the axial positions on each side. So on the left, since ethyl is axial, the total axial strain energy on the left is just 8 kilojoules per mole. On the right, I have two groups axial. There's methyl, which has a value of 7.6, and chlorine, which has a value of 2. So the total axial strain energy on the left, I'm sorry, on the right is 9.6. So since the one on the left has less total axial strain energy, this conformation is going to be more stable than the one on the right. And the equilibrium is going to favor the one on the left. Now I'm going to do one more example to kind of show you it's not always about what If there's multiple, if there's more groups equatorial, then that's automatically more stable. That was true for this problem. But let's look at a problem where that's not going to be true. So we have a methyl group, and then I'm going to put a tert butyl group right here. And then one more methyl group. So again, for convention's sake, I'm just going to number it in that way. And then let's draw our chair. And I always number it in this direction because I know in that upper right-hand corner, I know without a shadow of a doubt what's axial and equatorial. So on number one, that methyl is going up, so I'm going to draw it upwards. In number two, the tert-butyl group is up, so that's going to be equatorial here. And then number six, that methyl group is down, which is axial. I'm sorry, I mislabeled this one. This one should say axial. So I have two groups axial, one group equatorial. The common mistake students make is they automatically say, oh, the other chair should be more stable because I'll have two groups equatorial. Let's just draw it and then let's look at the numbers. So I'm going to do a chair flip. Number one becomes the footstool. Number four becomes the headrest. And then let's put our groups on. So number one, the methyl is now equatorial. Number two, the tert-butyl group is now axial. And number six, the methyl group is now equatorial. So let's look at the axial strain energies. So for methyl, at 7.6 kilojoules per mole. For tert-butyl, it's 22.8 kilojoules per mole. So let's look at the total axial energy for each side. So on the left, you got a methyl that's axial. That's a value of 7.6. And another methyl that's axial, 7.6. So the total axial energy on the left is 15.2 kilojoules per mole. On the right, the only group that is axial is the tert-butyl group. But look at how massive that axial energy is. That's 22.8 kilojoules per mole. So the total axial energy on the right is bigger than the one on the left, even though the chair on the right has more groups equatorial. We would say the equilibrium favors this side. That is the more stable chair conformation. So you can't always say the more groups equatorial, the more stable it is. You have to look at the axial energies. All right, we just have a couple more things to talk about before we conclude this chapter. The last thing we're going to look at, and this will lead into in one of our next chapters, is we're going to look at a new type of isomer called a stereoisomer. Now, a stereoisomer these are isomers with the same connectivity. I want you to circle, highlight, star that, because that's different than a constitutional isomer. But what makes them different? If they have the same connectivity, but they have different three-dimensional arrangement of groups around one or more carbons. Now, to illustrate this, let's look at cyclohexane, and we're going to put two methyls on it, both going upwards. And I'm going to draw on the hydrogens as well. Now, what I'm going to do, and I recommend try this with a model kit. I'm going to physically take this CH3 off and switch places with the hydrogen. So I physically rip those two atoms, those two groups off of cyclohexane, and I switch them around. And now that CH3 is still up, but this one is down. So around this carbon right here, there is a different orientation in three-dimensional space of the CH3 and the hydrogen. On the drawing on the left, that CH3 is going up, and the drawing on the right, that CH3 is going down. We would call these stereoisomers because they have the same connectivity. If I were to number these carbons, 1 and 2, I still have methyl groups on 1 and 2. I didn't change the order the atoms come in. I just changed what direction the atoms or the groups were going in. And those are called stereoisomers. We're going to spend an entire unit on stereoisomers and stereochemistry. Now, on a ring like this, if two groups, and I'm just looking at the relationship between two groups, if two groups are going in the same direction, we would call this a cis isomer. If they're going in opposite directions, we call that trans isomer. And it's important to make sure that you put those in the names when you name a stereoisomer. Because if you want the reader to know that in that cyclohexane, the two methyl groups should be going in the same direction, we start off by putting that term cis at the very beginning. So you would say cis 1,2 dimethyl cyclohexane. And then the one on the right, we would say trans 1,2 dimethyl cyclohexane. Okay, and we're gonna, as I said, dive a little bit deeper into stereoisomerism in a unit very close or very soon. Now, the last thing, I promise this is it, that I want to highlight that's kind of unrelated to anything we've talked about in this chapter. But I want to start talking about the concept of functional groups because it's already come up in lab and it's going to kind of come up in our discussions later. Functional groups allow us to categorize the millions upon millions of organic molecules, and it allows us to kind of conveniently put them in a family based on a common group or a common atom. So, like, for example, if two compounds have an OH group in them, we call that compound an alcohol. So they might be two different alcohols, but they're in the same family because they both have an OH group. If you have a carbon-oxygen double bond that's surrounded by carbons, so R here is my kind of lazy shorthand for carbon groups. Could be one carbon, could be 100. It's just a generic set of carbons. That's called a ketone. If there's a hydrogen on one side, not a carbon, we call that an aldehyde. If there is an OH group bonded to a carbon-oxygen double bond, we don't treat that as, oh, that looks like a ketone and an alcohol. No, it's not two groups put together. This whole group by itself is its own specific type of group. This is known as a carboxylic acid. Now, closely related to that is if instead of a hydrogen, you have another carbon group, we call that an ester. Sometimes some people refer to it as a carboxylic ester because they're typically made from carboxylic acids. But if you just want to call them an ester, that's fine. Now, if there's a nitrogen bonded to that carbon-oxygen double bond, that's called an amide. Amides get a little kind of weird because you could have one carbon attached, or you could have two carbons attached, and it's still in the same family as an amide. What you're looking for is this right here represents the amide functional group. A kind of related to that, sort of related, is a nitrogen bonded to carbon. Those are called amines. And like amides, you could have one carbon group on the nitrogen, or you could have two carbon groups on the nitrogen. They're all considered amines. So a nitrogen bonded to a regular like sp3 hybridized carbon is called an amine. And then the final functional group that I want you to know, we'll add more to this list down the road, is if you have an oxygen single bonded to two carbon groups. That's called an ether. Now, at this point in time, all I want you to be able to do is if I give you a massive compound, a massive structure of a massive compound, you should be able to pick out the functional groups and label them. So I think I put a problem like this on your homework set where you got a big molecule and I just want you to identify what functional groups are there. All right, and that will conclude it for this unit. I will see you on the next one.